All right, so today we are going to learn about Graham's law. So, Graham's law of effusion. Before we cover the law, I would like to explain the difference between effusion and diffusion. When you have two containers that have different gases, let's say I have CO2 here and I have oxygen here. So here are my carbon dioxide particles or molecules, here are my oxygen molecules, and now these two containers are closed. They have a lid on. So what's going to happen if we open the lid? Well, what's going to happen is that these gases are going to spread. So they're going to get out of the container, and that's called diffusion. So the spreading of a gas from a large opening is called diffusion. Okay? Effusion, on the other hand, requires that we have a tiny hole, like a pinhole. So the escaping of a gas or gases through a pinhole is called effusion. Okay? So an example of this would be balloons. For example, if you get helium balloons or even air balloons, what happens to these balloons after a while? Well, they deflate. Well, where did the gas inside the balloon go? Well, it's escaped through similar pinholes from your balloon, because these balloons, even though you don't realize it, are porous. They have tiny, tiny pores. They're so small that you don't realize that that gases from inside the balloon escape unless you wait a few days. Also, similarly, when you have tire in your tire, well, it deflates after a while. Every now and then you have to fill it with air or nitrogen, and that's again because rubber that's made up that makes up the tires is also a little bit porous, so it allows gas to escape, not at a high rate obviously, but it's still you can see that it escapes after a few months. For example, you need to inflate it again. So this is diffusion and this is effusion. Now let's look at a container over here that has a mixture of gases. Let's say we have this here. So a mixture of gases, okay? Let me draw another one, for example, just this. All right, and let's say that these are oxygen and these over here are CO2. And if we are at the same temperature, so this container is exposed to the same temperature. And really, the same temperature also means these particles have the same kinetic energy, because the higher the temperature, the more energy you give to your gas particles, and therefore the faster they're going to move, and therefore you increase the kinetic energy. So same temperature means same kinetic energy. So same kinetic energy. And I write just KE for short here, and that's what I'm going to be using from now on. In physics, the equation for kinetic energy is equal to half mv squared. Okay, so if I have carbon dioxide and oxygen, I can say that the kinetic energy of oxygen is equal to the kinetic energy of CO2. Again, why? Because they're both at the same temperature, which means that they also have the same kinetic energy. And if they have the same kinetic energy, I can set this equality. If they're both at the same temperature, then the kinetic energy of oxygen is equal to the kinetic energy of carbon dioxide. Well, but I know that the formula of kinetic energy is half mv squared. Before I move on, let me just do something here. And let me quickly explain what m is. M is the mass, usually in kilograms. In chemistry, we can use instead molar mass. It does give the same numbers, same meaning. So molar mass. V is not the volume, you guys. V is the velocity. Velocity and speed are two different things in physics, but for us in chemistry, we can interchangeably use them. So when I say V velocity, I can also be talking about speed. Okay, so how fast they go, and m is the molar mass. So if I have the kinetic energy of oxygen is equal to the kinetic energy of carbon dioxide, because they both have the same kinetic energy, because they both have the same temperature, I can also write it as half of m, the mass of oxygen, times the velocity of oxygen squared, is equal to half of the mass of CO2 times the velocity squared of CO2. Wait, what? All right, let me say that again. What I did, again, we have the same temperature, therefore all the gases inside this container here, over here, they all have the same exact kinetic energy. We also, and if they all have the same kinetic energy, therefore I can write that down. I can write the kinetic energy of oxygen is equal to the kinetic energy of CO2. But I also know from the law of physics that kinetic energy is equal to half of mv squared, which means then that I can substitute these, or instead of using just simply say kinetic energy of oxygen is equal to kinetic energy of CO2, I can simply use the equation. So I'm going to say that half of the molar mass of oxygen times the velocity of oxygen squared is equal to half of the molar mass of carbon dioxide times its velocity squared. Okay. So then when you look at this, you can see that the halves cancel out, and I really end up having this. Okay. Well, this really means that if the mass of oxygen, the molar mass of oxygen, is low, the velocity will be high to maintain this, because the molar mass of carbon dioxide is larger than that of oxygen. And therefore, its velocity will be lower. Let me say that again. I want you to think about two people that are trying to run, and they both have the same level of same level of skill running. They've been training as much, they've been practicing as much, but one person is 100 pounds and the other person is 150 pounds. Which person will run faster, given that they both have the same exact amount of skills and practice? Usually you understand that the person who has less weight to carry will be moving faster. So it's the same idea. If I look here, oxygen has a molar mass, because oxygen's O2 is a diatomic molecule, has a molar mass of 32 grams per mole. Carbon dioxide, if you do the math, 12 plus 32 is 44 grams per mole. So you see that carbon dioxide is a bigger molecule, so it has a high mass. Therefore, it's going to move slower than oxygen, which has a molar mass that's lower than that of carbon dioxide, but its velocity is going to be higher because it's a smaller or lighter molecule. So the bigger the molecule, the smaller the velocity, or the slower they're going to go. If the molecule is light, then it's going to move faster. It's an inverse relationship between the molar mass and the velocity. So inverse relationship between M and V. Now, this is really Graham's law, but that's not the final version. It looks a little bit different. We tweak it a little bit mathematically, so it looks a little bit different, but it's the same thing. So basically what happens is you put all the molar masses on one side. So the molar mass of oxygen over the molar mass of CO2 on one side. And on the other side, you have the velocity of CO2 squared over the velocity of oxygen squared. And we don't like to keep squares in the equation. And therefore, it really is going to look like this. Now we do square root of the left side. We take the square. So we actually basically square everything here. So when you square everything, the squares here go away, right? And then this becomes a square root. So you get here the square root of the molar mass of oxygen over the molar mass of CO2 is equal to the velocity of CO2 over the velocity of oxygen. Okay. So this is Graham's law, but in a more general term, it's MA, because this is specific to a problem where we have oxygen and CO2, which we won't necessarily have. So it's MA, gas A, over the molar mass of gas B, and you take their square root, and this is equal to the ratio between the velocity of gas B over the velocity of gas A. When you're writing Graham's law, it's very important to realize, because it's an inverse relationship, that the molar mass of the gas that you have here on top means that on the other side, it will be the velocity of the other gas, of the same gas on the bottom. Let me say that again. If you have gas, the molar mass of gas A on top on the left side, then on the right side, the gas A is going to go on the bottom. You're going to have to divide by the velocity of gas A. If you have gas B on the bottom here in the left in the molar mass, then the velocity is going to be on top here of the ratio on the right side. With that said, you guys can rewrite it. This is the same thing as this, so you can do that, and you can actually verify it with numbers. So VA here and VB over here. It's the same thing. This and that is the same thing. It doesn't matter where you put A or where you put B. What matters is that you keep the relationship here. If you have A on top over here, you're going to have V on the bottom here. If you have B on the bottom here, you're going to have B on top here, etc. If you have B on top, V is going to be on the bottom, etc. That's what's very important. And when you're solving, if you're supposed to be, when you're solving for one of the variables, make sure to put that x or that variable on top. You're less likely to make mistakes that way. So this is Graham's law of effusion.